Okay, hi everyone. So we're going to solve question avoid division in Coder beginner contest 453. We have a tree with n vertices. So a tree is a graph with no cycle, which means in a tree, when you pick two random vertices, there will be only one path that connects those two vertices. We have n vertices, which means we have n minus 1 edges with one edge is basically the path connected by two vertices ui and vi. We have k colors running from 1 to k, and each color can be used ci times, which means, for example, if c2 is 4, it means that color number 2 can color at most 4 vertices in our trees. So we have to check if our tree can satisfy this requirement. For every edge, there exists some color I, such that both of the two subtrees obtained by cutting the tree at that edge contain at least one vertex colored with color I. So I will rephrase it by we have a tree, right? So it asks whether it is possible that when we remove any random edge, this tree will become a two different subtrees. So we have to check whether it's possible that there will always be a color that these two subtrees have in common when we remove any random two edges. Sorry, when we remove any random one edge. So as can be seen for our constraints, most of the variables run from 1 to at most 3 multiplied by 10 to the power of 5, which is still in the range of C++ integer, so I'll use integer. As can be seen, we have t-test cases. Here we have two test cases and n vertices, k colors. The colors will be marked by, well, an array running from 1 to k. Here we have 3 colors, and each of them can be used 2 times. So our output will be a color array. For example, vertex 1 will be colored with color 3 and so on. So if there is no valid coloring possible, we'll output -1, which is understandable. Okay, I think I get the problem. Let's implement it. Okay, so let's get started. std, so main. We'll have t test cases, and it runs from 0 to t. Actually, it's better if I just use while loop. So let's implement, because we have to solve things, right? So I'll just put everything in this function solves right here. So we'll just call it right here. Sorry. Yeah, I think so. So now we'll need I'll just store the link of the problem right here because we'll need it later. I'll just push it on GitHub so that I can like revise later on. This is avoid division.cpp. This will make later like running far easier. Let me paste. Okay, here we go. Oh yeah, and main.execution. Okay, so firstly we have n and k, right? With n is vertices and k colors. So we'll build a tree using adjacency. Well, build the tree using adjacency list because we have the start and the end of the vertex. So I'll just store like all the neighbors of one vertex. It will make it easier to track the edges. So I'll build the tree. We'll use something called adjacency. Am I writing that correctly? Just never mind. List. So it's a vector. Oh yeah, we have to include vector right here. Oh man. Okay, JSON C, and we're going to have n slots. Yeah, n slots. So it runs from, I don't like, let me see, it runs from 1 to n minus 1, so it's less than n minus 1, I plus plus. Yeah, that's right. I think that's how we do it. Okay, so we'll just store it by, well, receiving U and V, and then we decrement it because we're using zero-based system, numbering system. Let's, okay, initialize them, C in them, and decrement them. Oh, I typed wrongly so much. So adjacent U, pushback V. Similarly, we have V right here and U right here. Oh, and because this is a vector, a store vector inside, so it has to be a 2D array, 2D vectors. So now we'll have to count the leaves. Oh, let me just do things step by step. So this is adjacency list, right? So the strategy is that store the neighbors of each vertex in a vector. Yeah, that's pretty fast. So next we'll just do things like color the leaves and color the remaining vertices. So we have strategy right here as well. Our strategy is that, what is our strategy? I don't know. Let me think. Uh, okay, we'll need helper function. Firstly, we'll need paint leave, which is, we'll use it for update the unpainted leave. Um, we'll have the group of leaves. So here we'll have to group leaves into groups cluster. Yeah. And we have the colors. We paint, update unpainted leaf. We'll have color the leaf, the leaf in the specified group with color I. And to track the leaf, we'll use priority queue to track the leaves in each group. Strategy is that use priority queue to track the group with most unpainted leaves and we specify the leaf using pointer. So we'll need a vector pointer right here. I think it should be around here. The leaves in each group with pointer. To track the leaves in each group. Okay, so how do we cluster leaves into groups? Strategy, we'll need a vector to store the index of each group, initialize the index equals 0. And next we have to cluster the leaves into groups. So how do we cluster though? Let me see. Okay, we'll use DFS, depth first search, to cluster them into groups and check if the vertex is leaf. Um, store them in groups. How do we store them into groups though? Yeah, they'll just be vectors of leaves, right? Yeah, it's fine. So store leaves into a vector, and then we store vector of leaves into groups. Also, this is a 2D vector. So to do so, we have to find the leaf centroid. The strategy of this is that iterate in post order to find the vertex satisfying the following condition. Firstly is that satisfying. Firstly is that it creates an upper part with less than or equal to L2 leaves, create other subtrees, not upper part, with less than or equal to L minus 2 leaves. Initialize centroid equals -1. Assign centroid with that vertex and break. Okay, so if we find a leaf centroid, then we have to have the number of leaves and sub-leaves first. So we have to build the tree. Well, we have to like build sub-leaves, parents, order using DFS. So we do recursive DFS, a random root, initialize root equals 0, 1. Just find a random root. It's easier, right? Okay. And recursive DFS starting from a random root. And after that, what should we do? We should keep. So what is the base case? Until we find the leaves. Oh no, actually no. Until what? Let's see. How do we iterate? I see. Let me see. Yeah, until like until we meet the leaves. That's true. That's true. So post order. Tracking. Yeah. Yeah, I think that's correct. So now we count the number of leaves. Okay. count the number of leaves. That's right. Okay, so number of leaves is L. Yeah, L equals -1. No, 0 because we increment it up. We traverse through all the vertex. So if it only has one neighbor, which means adjacency size equals 1, then it's a leaf, right? So if it's greater than 1, then continue. If not, then we increment L by 1. Okay, I think that's correct. And next we build subleaves right here using DFS. Oh, if so, then we have to have functional library. Yeah, this is for DFS right here because, well, I'll just write auto first and you will see why we have to use a functional thing. This is a lambda expression, right? So I'll call the DFS equals something like, so inside here, oh, we have to find the random root first. Forgot about that. Equals -1. It's very simple. We have to check if it's not a leaf, then it can be a root. Because if we use like a leaf for DFS, it'll be very weird, right? So how, like, it'll be very weird. It's computationally inefficient. Okay, so we have I running from 0 to n, that is the number of vertices. So let me say if adjacent of I, oh yeah, right here should be, okay, I think V is better. V is better word because it's vertex. So I'll call it V. And here is, I'll call it V as well, right here. Okay, size. Um, okay. Oh no, actually. Oh no, 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 no. Let me just, yeah, it's better if we do it like this. We break. Yep. Okay, now we have the root. So what should we do with the DFS? So we have to find a random root, which we have done already, and we have to do recursive depth first search, starting from a random root until we meet the leaves. And we have to like build the parents array. So we have to track for each vertex what is its parents and the subleaves of each vertex. Like if that vertex is the root, then what is the number of leaves that it has? The least number of leaves is 1, including itself. So, okay, we have something like sub sub leaves, and there will be, I don't know, for each vertex, right? So it's n, and every of them will start from, um, I don't know, should be, how many should it be? 0, because it should be 0 because we can set it to 1 inside and we increment it. So we shouldn't risk setting it to be 1 outside. Next, we have parents. It has n and it's initially it's -1 because, well, there's no parents, so -1. 0 is a vertex, so we cannot set it to 0. We have to set it to -1. Finally, we have order. I just not put it inside, like we will not initialize what it is size because it's not necessary. So, okay, for DFS. Okay, I think that's enough. So we have to, so let me set it up. We have root, right? And the parents is -1, right? Previous. Okay, so we have int v and int p right here. P is for previous. Previous or parents is up to you, but I like calling it previous. Okay, so DFS. Interesting. Let me think how we should. Okay. Okay. So I'll just traverse to all the neighbors of V. Oh, yeah, this should be this one, square brackets. So if U is a previous vertex, and we have to continue because we don't have any cycle right here, so that is a cycle. That is when we know that we reaches a leaf. Oh yeah, so how do we check if a leaf is a leaf? Okay, so continue right here. This is a leaf, right? We break because we reach a leaf. So just imagine that initially we have something called is leaf equals true, and if it passes this condition, which means it is not a leaf, then is leaf equals false. And outside if is leaf is still equal true, which means B is a leaf, then we'll just set subleaves of V to be 1, which is itself. So inside here, we will call DFS recursively to U and V again, which we'll see the problem right here. Auto function does not allow recursive calling, which means we need to call it as void and int because well, the input is 2 integers. So now there's no problem anymore. Oh yeah, by the way, this is, let me see. Oh, I'm bad at this. Okay, syntax. Okay, yep, that's correct. So for the subleaves, how should we calculate it? Subleaves, I think it's easiest to just call it like this. V plus subleaves U. Yeah, that's right. So you just call it back to the end, and then we add it up like recursively. So it's like to the end, and we add to the end to the top. So run it back. It had to be after this recursive call. So now we have to create the order. So after we run to the end, then what should we do? Yeah, it's the same. After we run to the end, we will construct the order back because it's sub order, it's post order. So push back the, I see. That's right. That's right. I think that's right. Yep, I think that's right. Okay. Is that so? V and post order. Yeah, I think that's correct. Okay, so find the leaf centroid. Let's see. Initially, we set it to be -1, and we traverse to the order. So int v order. After that, we will check. Okay, so how do we check it? For the upper part, right? And for the remaining part? How do we check the upper leaves? Oh, it's very simple. So we have L minus the subleaves of the current vertex, which will create the leaves of the upper part. So I'll just call it something like satisfy is a boolean because it's true or false. L minus subleaves of the current vertex. So it will be less than or equal to L minus 2, sorry, L over 2. If it's not satisfied, and we'll just simply continue. If it is satisfied, then we have to check the remaining part. So how do we check it? Yeah, we'll just iterate through all the neighbors of V, the current vertex. Okay, and if U equals to the parents of V, which is the start of the upper part, then we'll have to continue. Else, okay, something's wrong right here. Yeah, that's correct now. Wait, did I update the parent before? Parents. I didn't update it here. Oh, that's a deadly mistake. So we have to update parents right there. So just do it from the beginning though. It's fast. There's nothing special about it. Okay, we have U and V and continue. So if not, then we have to check if it satisfies this condition right here. So L minus sub leaves of U is more than L over 2, and we have to continue as well. Or else, then we can just set it to be V and we break. Perfect. So that's how we find a leaf centroid, right? Oh no, I don't think so. Yeah, oh no. You have to put it outside the break, right? Yeah, is that so? Yeah, because we have to check all the parts first. Oh my God, that was so dumb. So, no, I don't think so. So this should be like 0. Like, yeah, it should be like satisfying equals 0 equals false. And we break. Actually, I don't like this format at all. Just delete it all. Yeah, then we add it again right here. And we break it. And the outside, we have to check again. So if it's satisfying, then we set x to be v and we break. If it's not satisfying, then there's a problem. Oh yeah, oh yeah, I just think of a problem. What if our tree just have 2 vertices or 1 vertices, 1 vertex? Oh yeah, that's right. That's right. So if there's 2 vertices, we have to color them with the same colors. If it's like 1 vertex, sorry, let me see the range of the vertex. It runs from number of vertex, it runs from 1 to, oh, number of vertex, it runs from 2. So at least 2 vertices. So if there are 2 vertices, we have to color them with the same colors. So let's handle this case right up here. Build a tree adjacency list. Hmm. Yeah, I will. Should I? Yeah, I will just put it right here. I don't know if there's a test case that easy, but I think like if we handle it, it'll be safer. I think so. Oh, yeah, and we did forget. Oh yeah. Oh yeah, oh yeah. Oh, actually, we have to put it down here. And yeah, we forgot to input. We have to save the colors. Okay, so right here we have to check versus case. Okay, so if there's like only 2 vertices, what should we do? Hmm. We have to find if there's any color with at least 2 available numbers, right? So it's not hard, it's just like this. So int color equals like -1. So if it's, we just add it up. So let me see. Yeah, nothing special. So I just set it to be -1, and okay, okay. I think of the solution for k plus if ci is greater than or equals to 0. No, just make it like this. This is C, right? Prick. Sorry, not prick. Continue. So if it's not, then we just set color to be I and we break. Okay, so if color equals -1, then we see out -1 and line return. And if not, then we see out color, not color. Should I? Yeah, color. And line return. Actually, this return is redundant. Boom. Perfect. So that should be how we handle 2 vertices. So now we have the leaf centroid, right? This is the leaf centroid. Yep, we have the leaf centroid already. Interesting. So now we can group the leaves, like cluster the leaves. I'll create a vector to groups, and we'll do DFS as well. So we need a function, same as before. What's wrong? Oh yeah, I'll just call it collect. Wait, but how do we do it though? Correct leaves. Oh yeah, because from the centroid, if we remove the centroid, then it will become like, for example, if the centroids have 3 neighbors, we remove the centroid and we will create like 3 subtrees, right? So we have to iterate through each neighbors of centroid, and we use that neighbor at the start of the new subtree. So we'll use depth first search from that start to check how many leaves it has and store it into the groups, right? So actually, we should delete this for end. Just call it start and adjacent of x. So, okay, function will be inside here actually. I think so. And boom, bap, tick, boom. So in V and previous P, similarly. What's wrong right here? Yeah, forgot. Collect. So some crazy thing happened inside here. So what should I do right here? Start from adjacent of x. So we should have a vector to store leaves, right? Storing leaves. And the purpose of this function is to update the leaves, store the leaves of each subtree into leaves, right? Okay, so how should we do it? How should we do it? Interesting. How should we do it? Okay, we just do deep depth first search and we call the function again and again until we meet the leaves and we store the leaves into it. Okay, so now how do we store the leaves into groups? So we have to check if it's empty or not, right? If it's not empty, we'll store it to our groups, right? And because this is a vector, so here this had to be a 2D vector, 140. Okay, so groups, push back, leaves, boom. That's how we do it, baby. That's how we do it. Yeah, I'm being so high. So yeah, we should output. Nope, nope. Size of the groups. We'll need it later. I think so. Boom, bap, take two. Okay, so we have the purpose. So how do we implement this? Similarly, before I think we have to, because this depth first search, we have to, oh yeah, outside, out, and go through all the adjacent of V, and if U equals the previous, then we continue because we don't want any cycle Oh, by the way, if we do it like this, we have to start somewhere, right? Yeah, forgot about that. So start with start and centroid. So if it's not cycle, if it's not a parent, call it on U and V. Right. So this is a leaf, mission of a leaf. So we technically don't continue right here, right? Yeah, we have to add it to the leaves. Oh, condition. Leaves. Oh, I wonder if I can boom, bap. Nope, nope, that doesn't work. Sorry. So we have the condition of a leaf. So okay, we can store it into it right here, I believe. Or do I? Oh, actually no. Actually no. No, 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 no. No, I don't think so. Should I? Should I though? Let me see. Let me think. Let me think. Hmm. U equals P. And it's the parents. It's leaves before. I don't think so. Yeah, I don't think so. Because you know what? If U equals P, it doesn't mean that V is a leaf. It's just like one of the K's. So no, we have to do it separately. This is actually continue. Yeah, 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 that was a dumb idea. Leaves should be pushed back right here at the end, sorry, at the beginning. If V only had one neighbor. Yep, that's how you do it. That's how we do it, baby. That's right. That's right. So we collect it right here. Yeah. Should I do anything more crazy? Oh, by the way, why do we put it inside here though? That was a dumb idea. Yeah, it should be outside. Yeah, 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 yeah. That's right. That's right. That's right. Okay. I think that's it for lambda function. So we don't really need a purpose right here though. So it's just simple command. Oh my God. Yeah, simple command is enough. Boom. That's it. You don't need like crazy stuff for that. That's it for the grouping function. I think that's it. There's nothing special about it. So we have to create a pointer to track the leaves in each group. Just call it vector and int pointer. Just call it PTR, it's better. So right here we have like G groups, right? And each group start with index 0. That's right. We track the leaves in each group and we color the vertices. So how do we track the leaves in each group? We have to use priority queue. That means we have to implement queue right here. This is for priority queue. And because we store two things inside this queue, firstly is the number of unpainted leaves. Secondly is the name of that group 1, 2, or 3. So we need to pair, and thereby we need to include utility to use pair because I don't want to create a struct. It's it's lengthy. I'm lazy, man. I don't want to create a struct for pair. Just want to use something that's available for me. I'm that lazy guy. Okay, so where were we? Where were we? Oh yeah, here we are. So okay, parity queue. Boom, pair. Boom, 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 boom. We have PQ. That is short for parity queue, of course. So how do we set up this? How do we set up parity queue? I don't know. Hmm. So we have two components, number of unpainted leaves and the group names, which is the numbering of groups. Blah, blah, blah. I'm being dumb, sorry. I think you just iterate through each groups, right? We have like G groups, so we iterate from through each groups and we store the signs inside. Yeah, that should be how we do it. Push in a pair. So we what do we have? We have groups G size, and this is what is this? G. Is that so? Perfect. I think that's correct. Like, how could it be wrong though? Oh, there's one space. I want to delete that. So that's the tricky thing. Color the leaves. How do we color the leaves? The strategy, okay. Strategy is that we will color the two groups with greatest number of unpainted leaves with the same number, same color. Use same color for the two groups. Yeah, that's right. This should be capitalized to make it better. Yeah, I'm crazy with formatting, guys. So after we color two of the most, like two greatest number of unpainted leaves with the same color, why do we do it? So imagine we have like five groups. So if you just color them randomly, then eventually the group with the most unpainted leaves, they will be left with the most number of unpainted leaves, and we have no remaining groups to solve this problem. That's why we have to choose the two most unpainted, two most like groups with greatest number of unpainted leaves, and we match them first, we connect them first, and after that we'll do something called shrinking. It means that we'll just iteratively like spam the same color for the largest group in each run. So in each run, the number of unpainted leaves in one group will be decremented, right? So the group with the highest number of unpainted leaves may change after iterations. So we just like use priority queue. We leverage priority queue for that characteristics to have the group with the highest number of unpainted leaves at each iteration, and we paint them with the same colors. So we spam the same colors for group with max number, not greatest number of same at the above. So yeah, I think that's it. So what do we need? We need Spider-Man. No, we don't need Spider-Man here. We need so something like unpainted to track unpainted leaves. Okay, that's a dumb name, but you know it works. Unpainted leaves. Track number of. Next is what do we need? We need RAM to track number of remaining color because you know every time you paint the availability of the color decreases. You have to track that as well. What else do we need? What else? I think that's it. Yeah, I think that's it. So let's implement this. We have variables in strategy. We have everything except the implementation, which is the most important thing, ironically. So as I've said above, we need to helper function. This time is not like recursive function, so we can just use auto. So we have paint leaf equals something like just this, and we have what do we have? Get leaf, get top. Because you know what? For priority queue, every time we pop and push, the greatest number of like leaves, unpainted leaves, can be different in each time. So we have to use get top to clean it and make sure that it's get updated with the new number of unpainted leaves. That's very important because we do so many things outside of the function, and we have to keep track of it, or else it'll just be a mess. So I'll just do something like this. Spider-Man, Spider-Man. So paint leaf, it'll just paint, so it's a void function, so which will not return anything. For get top is not a void function, will return the two components of the priority queue, so we have to return a pair. Yes, right, we return a pair. Yeah, that's it. So now we have to implement the coloring stuffs. So I'll just iterate through each colors and we'll brainstorm what should we do for each case. Hmm. We have K colors. So in general, what should we do though? Yeah, we should initialize unpainted as I've said above. Unpainted is, what is this? It's L. L is the number of leaves. Next we have rem, which is the availability of the color I. Perfect. I'm being dumb, sorry. Okay, so we have to track while unpainted because we have to paint all of them is more than 0, which is there are still unpainted leaves, apparently. And rem is more than 0 to be sure that we're not running out of colors. So unpainted and rem. So our strategy is selecting the two most like crowded fruits with like unpainted leaves, right? So we have count 1 in group 1, something like PQ. Oh, actually just get top. Similarly, oops, yeah, this is for getting the two groups with most unpainted leaves. Okay, so when we get both of them, what should we do? We have to, what do we do? We have to pop, right? Yeah, yeah, we have to pop between because if not, we just return the same thing. We have to pop. Okay, PQ pop, PQ pop. After pop, we have to paint. And if we paint, the remaining color will be reduced by 2. That's very important. Shouldn't forget that. So we have paint leaf. We paint color G1. Sorry, we paint the point G1. Function, it will just be something like purpose. Paint the vertex of each group with color C. Okay, so the input will be G and C. Interesting. So we have I plus 1 right here because we use 1 base for the result. And paint leaf, similarly G2 with I plus 1. Interesting. So rem minus 2. And we have to push again. So how do we push? We have to check if the current index is in the range of that group. So pointer of G1 is still less than the size of groups G1, right? If so, then we will push PQ, push a pair. Firstly, it's the size. So how do we check the size? Size will be CNT1, count 1 minus 1. And because we paint one of them, so we have less, like the number of unpainted leaves will be decremented by 1. And G1 is the name of the group. Okay, that's correct. So semicolon, similarly, boom bap, AD right here. Yeah, I should change this to 1 by the way. Perfect. We have push. We pushed them already. What should I do next? So now we do the training stuff. Train the train the group with most unpainted leaf with current color wiring more than 0 and unpainted leaf more than 0 as well. Just color it. So we have count and G with PQ, no, get top. So we paint it. I plus 1, and with a paint we have to decrement the remaining color. So what should we do next? Pop and push. Push the count minus 1 and G. That should work. It should work. Oh yeah, I forgot to check the size though. Let me check the size as well. Let me see. Oh yeah, I think that's correct though. I think that's correct. Yeah, that's right. Check this thing. I think that's right. So wait. Oh yeah, I think we don't need to do this if the remaining color is enough for all the leaves, right? So in case it's enough for all the leaves, we can do it differently. Oh, and if the current color is like less than 2, for example, I think if it's less than 2, then it's no point. Just leave this to the next. I believe so. And honestly, we don't need to update this every iteration just to move it outside. And wait, this is continue. Yeah. If the remaining colors is enough for the unpainted leaves. What should we do? We should just spamming coloring. Count in G, and then we have get top right here. That's smart. No, not smart. Just kidding. So we push and pop and we paint. Paint first. And then we push. So we pop. We check. No. We check. Pointer is less than groups of G size. And then we pop. Oh, sorry, we push. -1 and G. That's right. Just like that. If we have more than remaining. Oh yeah, if we paint, we have to reduce the remaining color as well. Decrementing, that's very important. Very, very important. That's it. What else? Oh yeah. So if we have like only one unpainted leaves left, then we paint it with a centroid because we have no color left to match, right? So we paint it with a centroid. Should describe it right here. So if the unpainted equals 1, then we just have to color the current unpainted leaves with what? See? With the current color, color the centroid with the current color. Interesting. Interesting. So, okay. So I'll color it by, no, we don't need that though. Just paint leaf. Uh, actually, no. That's too long. No. So how do we get to the last leaf? That's a very tricky question. Just iterate through all the group and check the pointer of which group that is less than the size of it. That means that vertex is the last leaf, right? So it's just less than the last leaf, sorry, the size, then we paint it. It's too, like, I don't like the format of this thing. So just do it like this. Yeah, and if else, then color. Not really, we don't, we just need a G, right? That's unnecessary. So we break right here because we found it, and we paint, we set the color of X to the current color as well. So before this, we have to initialize the final array. I have n vertices, so n spaces, and initialize them with -1. That's it. And we should have break right here as well because it's the end. This is not necessary, but I don't know. Is it necessary? I don't think so. We break anyway, so that's necessary, unnecessary. So after painting all the leaves, we have to check if unpainted is more than 0, and then we just see out 1, and we end it. Return. If not, then we have to paint the remaining vertices. So how do we paint the remaining vertices? This is a good question. Very good question. How do we paint remaining vertices? Ugh. Just, why should I think about it though? Just spam coloring, right? Just spam coloring. Oh, what is that? Just did something stupid for sure. Oh yeah, it's my shortcut, sorry. Just my shortcut. So strategy is that spam coloring with the remaining color. So we need a vector to track the number of remaining color, right? Yeah, that's right. And then we have to track. Okay, so this is a 2 pointers approach. So the first pointer track the number of remaining color. The second pointer track the index of uncolored width, uncolored vertex. That's right. So I'll just call it used for, wait, what? Yeah, just call it used. This is to track the index, sorry, not index, availability of uncolored vertex. Perfect. So we traverse through all the vertex. Oh, this is not V, sorry. Uh, Jump here and we jump to, I think it's K, right? Is it so? And K, oh, it's N, sorry, N vertices. So we have to check it right here. Yeah, if what? If it has been used, right? So if color I is not -1, if it's -1 then we skip. If it's not -1 then we add how many times it's been used. And now it's just iterate through the remaining vertex. So while the number of remaining colored track, sorry. Oh yeah, I did the wrong thing right here. It's actually this should be a number and this should be a number of uncolored vertex. This is the index, not the number. That's right. Okay, so if we have to jump to available color, if use I is more than ci, or you know, um, okay, so we have to set up pointer to track. Hmm. So this should be ci and ci less than k is zero based. Oh yeah, just do something simple like ci++, increment it. Then we have to check to the uncolored vertex if color I is not -1, then we have to continue. Color I equals ci plus 1. That's it? I think that's it. It's very simple. It should be simple for something like this. I think so. I think that's correct. Oh yeah, we have to update the used I as well because we use it. That's it, baby. That's it. So now we just output everything, right? Color I. If I is not n+1, then we also see out this, see out n lined. Okay, that's correct. Perfect. I think so. I think that's correct. So now we have to debug. Yeah, I think that's it. Now we just have to debug. So let's see. Line. Oh yeah, we forgot to implement the two methods. Paint leaf. So how should we paint the leaf? Good question. We have to have the vertex and we have to update unpainted. Wait. Oh yeah, should be up here. That's right. So how should I do it? How should I do it? Firstly, you have to get the vertex, that is groups, G and pointer G increment for the next time. And color V should be C. I think that's it. It shouldn't be something difficult, right? Yeah, I think so. I think so. Shouldn't be something difficult. Forget top. I just don't like this a lot. For parity Q, we have to remember one thing very important is that we have to just iterate three conditions and check each of them. So while PQ is not empty, we have to do this until it's empty though. It's not empty. Or we reach a case where like it's matches the requirement. Um, we have to have the current count and group by PQ top. Should I do next? We have to calculate the actual count, which is calculated by, you know, the current group size minus the pointer, which will return the unpainted leaves. So it should be this way. And if there's no unpainted leaf left, just pop it down. Just pop it down. If actual is different from count, what should I do? I have to pop and push. Actually push actual, not CNT, not count. And finally, if it's the same, then we just return the top. You have to redo it until it's the same, it's correct. If it's not, like if everything is false and after like updating everything, we'll just have 0, we just have empty, then we turn 0, 0. Sorry, -1, -1. Should be this way. Should be correct. Should be right. False. Failed. Why does it failed? On what line? I don't know what line, but it's failed. Long, long, unsigned, the size equals failed. Okay, it's debug time. To me, this error looks very somewhat likely to like when you get to an like memory allocation that you have not allocated yet. So I'll just go through all the like initialization of vector to see if I forgot to put any important. We have n, we have k, we have n, we have n sub. Oh my god, wait, is it k, c? Yeah, that's correct. Sub leaves is for each n, we have sub leaves is for number of vertices. Parents for each parent, that's correct. Order is nothing but pushbacks. We don't need a number for spaces for that thing. Groups, for groups, how should I force groups? I don't know if it's correct, but we push back, right? We just push back. So we don't know the vector from the beginning. We don't have the number of vertices from the beginning. That's true. We just push back. That's true. That's true. Pointer will be G, which is the number of groups. Is that so? That's right, because G is, well, nothing special. Color is the number of vertices. That's right. And used is number of colors. That's right as well. Oh my god. I hope it did. I hope it wasn't right, but it was. Okay, so something's off right here. Maybe I store the functions incorrectly. Like I store the data incorrectly. Like color. Like maybe I store the color incorrectly. Maybe for the paint color. Let's get to paint color. Paint leave. Maybe I. Nope. Nope. Nope, nope, nope. That was correct. So for paint leaves, it always have to be I plus 1, right? It's 1 based. Always has to be I plus 1. And use, it has to be I minus 1. Oh gosh, I didn't realize that earlier. right? Because used, yeah, I think, yeah, that's right. That's right. This should be I minus 1. That's straight. This should be color minus 1 because it's zero based. I think that's the thing we're talking about as far as am concerned. Or do I? Because CI starts from 0. No, actually, CI starts from, yeah, I don't think so. I don't think so. I don't think so. Used, no, I do think so again. Yeah, I do think so. That's correct. Let me check. Still fail, but is it the wrong era? Sorry, the same era, but different era? Or different era? It's different era. Or is it the same though? I don't know. It's so dumb. My God. Yeah, it's the same error. Oh, that pisses me off. Oh, it's different era actually. Was it? Yeah, this is different era, so that did fix something. So previously it was that era, and now it's different era. So we did something correct. Okay. Vector allocator long unsigned. This size equals failed. So it was something wrong with vector and allocation, right? Interesting. Didn't think that would be the case, but yeah, it did. So we have used, we have color, probably this thing. Yeah, it was that one. Definitely that one. Was it? Is it the same era? Did it? Like, was it? I don't know. I just like spontaneously change it. I'm not so sure about that either. So we have color I plus one. It should be used color CI, right? Yeah, it should be CI, that's correct. Something else was wrong. Apparently. Apparently something else was wrong. I'm wondering what could be wrong right here because I actually runs from 1 to n, which is correct, and color is, I have to check color minus 1. Yeah, I think everything was correct. Like I'm down to everything. Hmm, that was very sus. That's very sus. So sus. Oh my days. How can I change it though? Okay, so color I was correct as well. That was so weird. That is so weird. So how could it be wrong? Where could it be wrong? I don't really know. Assertion this equals failed. Okay, it's time for debugging. Read line by line. Oh my God. I always love coding and I always love, sorry, always dislike debugging. It's two different things. But it's part of the process, right? We have NK, push, VU. It's gonna piss me off if I do something wrong here. So I don't want to do anything wrong here. Yeah, luckily I didn't. Wait, duh. This is quite dumb. How could I make a simple mistake like this one? Was it the wrong thing? Nope, still something else. Like we don't, we choose. Root date is not a leaf, of course. Why did I write it that way though? It was so stupid. That was so stupid. Oh my God. Yeah, that was so stupid. Parents P, true, V, sub leaves. Ay, let me see. Assign centroid with vertex. Oh yeah, centroid shouldn't be a vertex. So it should be a leaf, so just adding something. Everything is still correct. It just adds something that makes it better. I think so. I think so. I think so. I think so. Hmm. Wait a minute. This should be sub leaves. Oh my God. Still something else was wrong. Let me delete this. That's right. Okay. Keep going, guys. Something's wrong. Okay, so this is V leaves pushback. U of adjacent V, UP continue, collect UV. That's right, collect start X. If it's not empty, pushback leaves. That correct? That is correct. That is correct as well. This is so pissing. Oh my days. Pointer VG0, that's right. Priority Q is pair P perfect. For unpainted is L, right? And color is N minus 1. Oh my days. Paint leave, oh my days. Okay, I'm so sure. I'm so unsure where it could go wrong. Oh my goodness. This is so painful. So painful, brother. So painful. Oh my days. Let me see. This is unnecessary, but okay, let me just color X. Like I want to make sure it hasn't been colored before, right? Uh, just like be careful with it. I think it's more important. Unpaint it. Oh yeah, you have to redo it until. Yeah, I think that's the problem. Oh yeah, I see. Yeah, I think so. Yeah. So something goes like unpainted is more than 0. That's very important. Why didn't I think of that? Why didn't I think of that sooner? Oh my days, still wrong. My days. Actually have to check it right here. Like if either of them is -1, we have to break right away, or else it will be something very bad. Well, maybe that's a problem. Like, After a bunch of stupid debugging, I just realized, oh my god, that was so dumb. You know, we have a while loop here, but they never decrement it. So now we don't have the memory error anymore. Let me show it here for you guys to see. Oh, why did? Okay, yeah. What happened? Wait, how? Oh no. Tickatu. I bet you guys can't see it, right? So let me do it like this. Can you guys see it? Let's see. And you guys can see it. So here it's 1. So how do we fix it? It's very simple because we print 1. Oh my goodness. Boom. Now it's correct. Oh my days. Let me submit this. Yeah, that was everything. I hope it passed the test cases. If it doesn't pass the test case, we have to spend an extra like 30 minutes more, I think. That is bad. That's not something I should laugh about. Let's wait for it. Yeah, it's not passing all the test cases. It failed some test cases. Okay, so it just failed like 2 test cases when I submitted on Coder. So I think the problem might lie somewhere very simple. So we have to go like end to end again, head to tail again. Adjacency list, I'm very familiar with it. This looks correct. Save color, this is special case. -1, -1, -1. Color, wait, color is 0 based or 1 based? Oh shoot, color is, oh yeah, color is 0 based. This has to be color plus 1. Okay, keep going. We have leaves, that definitely correct. If not, then we would have failed so many test cases if that was wrong. Same for this, it should have been correct. Is it? Not a leaf. Yeah, it's correct. Subleaves. That is correct. Now we have to check the 2 helper function f, not like check them very carefully. I think somewhere in that. So unpainted, decrease s, vertex, increment pointer, color it. C is input, so all correct, 1 based. Get top, if, else if, wait. Oh man, this should be else if. That was dumb. Okay, so logic in here has been checked very carefully already. So we should check the coloring the vertices right here. So see how this is correct. This is probably correct. This is probably correct as well. Oh wait, something. Wait, CI. So use as, oh my god, that was very elementary mistake. CI should be checked before you, like, this could lead to like memory allocation error. Of course, why didn't I think of it? Should be like this, right? Then main. I think everything's correct now. Let me. Okay, so at present the code is running correctly. Is at -1. But I want to experiment a little bit, so let's delete this test case and we'll create a new test case. Just a simple one. I want something like this. The root, 2 leaves. So like we have 3 vertices, right? And let's give it like 2 colors. So no, just 1 color. So 1, 2, 1, 3, and you know, let's give us like 2 availability. What is this actually too easy? So how about like 4 colors? Like 4 colors? but like one each. So it's like technically impossible, right? Is it? Because for each edge, if you remove any of them, then you need at least two colors to connect the subtrees. Yes, -1. So if I just change one of them to like 2, it should be possible. Wait. Why isn't it possible? 1, 1, 1, 2. It should be possible, man. Let's see. 1. So I delete this one. Just 2 colors. Should be possible. Why is it impossible? Spider-Man, 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 oh Spider-Man. Something's wrong. Oh yeah, I forgot to copy it. That's why. Should copy it first. See? Black magic. Black magic. Possible. Tell you. Told you. Let me submit this. See, baby. See, it passed all of them. But we have some warnings up here. These warnings actually like compare it to the size. There should be like integer right here to convert it into integer first. Because if not, it will be a long integer. So yeah, we should take that in mind. But it's not a big deal. Oh, passed. Okay, so I think that's it. So now let's go through the codes one more time. Okay, so what was it? Wait, where is it? Yeah, I see it now. Okay, so firstly, we build a tree using adjacency list. Basically, this helps to capture the essence of a graph, where for each edge you can go from either U to V or V to U. So we use adjacency list to capture this, and after that we have to save the colors. So next we handle the two vertices case, which will benefit a lot if we, well, realize it soon, and count the number of leaves. Oh, actually for like um, two vertices case, there is no leaf centroid, so we need to implement it in the beginning so that we don't run into problems later on. So count the number of leaves so that it helps us to find the leaf centroid. And next we use DFS algorithm to build the vector of order of parents and subleaves. And after having the subleaves, you can find the leaf centroid using the number of total leaves and subleaves vectors. And next, what's it is next? We cluster the leaves into groups using, like for example, if we remove the leaf centroid, then the number of subtrees created will actually the number of the centroid's neighbors. So just iterate through the neighbors and use DFS to count the number of leaves and store leaves into vectors. And eventually we check if the leaf vector is not empty. If it is, then we just save it into the groups. And we have to build a pointer to actually track the index of each leaves in each group. So next we use priority queue to leave us with the groups with the most number of unpainted leaves, which is very important because we want to make sure that we color the groups with the most unpainted leaves first, or else it will be at the end there will be the case where there is no um, groups left for us to pair with the largest group, which is bad. We don't want to run into that problem. So next we have two helper functions, paint leaf and get top. For get top, it's very important that we use else if right here, or else you ran into problems that I ran into. And we have to pop and push, make sure that you do it correctly and return -1 right here. This is not very important, but in some edge case, it will prove its value. Next, we will have the main loop for painting the leaves. We have three main cases, actually just technically one, because there's just one strategy is that for every iteration, you choose the two groups that have the most number of unpainted leaves and you match them with the same color. After that, you drain, like D-R-A-I-N, train the group with the most number of unpainted leaves to the current color to shrink the size down so that we won't run into the problems of like not having matched pairs that I've told you before. So when we do this, we realize that it's easier if we handle two extra cases. First is that there is only one leaf left. We match it with the same color as the centroid. Like we color the centroid and the last leaf with the same color. It's fast. The second is that the remaining colors of the current color has enough availability to color all the remaining leaves with that color. So we just spam, pop and push, paint, pop and push, and paint. So yeah, that's the main loop for painting the leaves. What about painting the remaining vertices? Similarly, you create a vector of used colors to track the number of availability of vacancies in the colors. And after that, you use two pointers approach to color. One pointer is to track the availability of the remaining colors. One pointer is to track which vertex has not been colored yet. Finally, the main loop. One important thing is that remember to decrement t if you use while loop, or else you will run into problems that I did. And if you don't want to like think about it too much, use for loop, but to me it's not as fancy. So that's all the things I want to like point out in my solution. This is a very, very inefficient solution, very, very lengthy and wordy. I don't think this is like this I don't think this should be how the problem should be solved because to me this is not smart. This is just like very like muscle heavy. I just did a bunch of things right here, to be honest. I think there should be a better solution. So if you found out a better solution, I'm so happy to know it. I really hate my solution, but at least it worked. So yeah, that's it. Thank you so much for watching and have fun. Choo!